welcome to the video. Today I would like to talk about forces on particles, and here especially on drag force, because in the previous videos we already balanced some forces and took a look how forces act on settling particles, and the drag force appeared there but in a very simplified way. And in this video I would like to give a little bit more insight into the drag force for particles. So the idea of the video is that we first get you get you get to know the general drag equation from fluid dynamics. So we will take a look at this equation, discuss the equation, then we discuss the Reynolds number. I think most of you know the Reynolds number, but it's really important. So this is why I would like to repeat it here and talk a little bit about the Reynolds number and how it's related to drag. And at the end, you learn about different flow regimes and how we describe drag in these different flow regimes. So the drag force in general is an umbrella term. So drag force is a resistive force that acts opposite to the relative motion of an object through a fluid. Could be air, could be water. So if you have any kind of object like this rubber here, and it goes through the air will resist this motion, and this resistive force, this is what we call drag force. And this is what you know when you go with a bike and you feel the air is pushing you, or if we go swimming you feel it different, right? In swimming the drag is much higher because you're in water, and this drag force is caused by the friction of the fluid against the surface of the object and by the pressure difference in the flow around the object. So, and here is what I already mentioned, the umbrella term. So we have two effects. One is the friction of the fluid, right? If I go through air, there's air friction on my skin, and this friction will create a resistive force, and in water this will be much stronger because the density is higher, different viscosity. And then there is also a pressure around the body, and this pressure is not completely homogeneous, so there is a pressure difference, and this is a second term. So the pressure difference in the flow creates a drag force, right? So, and here is a simulation we did in our group. So this is a X-Wing from Star Wars, and also if the X-Wing goes through air, in some of the image parts in the story, the X-Wing is not in space is no air, so in space is no drag, but in some parts they are fighting on a planet, and then the X-Wing goes through the air, and then there is some friction. And also you see here behind that it's not perfectly laminar, and this means there is a pressure difference, and this pressure difference creates a suction behind the X-Wing, and this is also a resisting force holding or pushing the X-Wing back. So here's quite nice the laminar part, and then we have here a low pressure regime which causes suction. Okay, so this is very general about drag force, and we have a fundamental equation describing these drag force, and this equation is different than in the last video where we calculate the settling velocity, and after this video you also understand why. So the drag force consists of the density of the fluid divided by 2. So this is the density of air, the density of water. Then we have the drag coefficient, and this is the key variable basically, because the drag coefficient is a function of the Reynolds number, and we don't know the function, right? We don't have CD Reynolds square. So if CD would be Reynolds square, we could write here Reynolds square. If CD is a function Reynolds plus 1, we could write here Reynolds plus 1. But at the moment we don't know this function, we just know CD is a function of the Reynolds number. So at the moment we cannot solve this equation because we don't know what to write in here. Okay, and that's the basic trick with the drag force. Pi divided by 4, okay, that's easy. That's the diameter of the particle. So Keep in mind, we don't calculate X-wings, it's too complicated, and in particle technology we don't have many X-wings. So what we normally calculate is particles, and particles are assumed to be a sphere, and this term here is basically the cross-sectional area of a sphere, and the area goes into the drag, and therefore we can write it as pi divided by 4 particle diameter to the square. And then also we have the velocity squared of the fluid. Basically it's the relative velocity. So for the drag force, it doesn't matter if the particle moves and the air is still, or if the air moves and the particle is still, or if both move. This is always the relative velocity between the objects. So if you have a steady particle and you have wind, you will have drag. If you have a steady fluid which does not move and the particle settling, you will have drag. So to work with this equation, we need to find a solution for this part here, right? For the CD as a for the drag coefficient as a function of Reynolds, and therefore we should first talk about the Reynolds number shortly. And the Reynolds number was basically described by Osborne Reynolds in his very famous paper, An Experimental Investigation of the Circumstances which determine whether the motion of water shall be direct or sinuous, and the law of resistance in parallel channels. So basically, in this paper he described basic difference in the fluid behavior in pipes, focusing on laminar and turbulent flow. And the laminar and turbulent flow is what he calls here direct and sinuous. And I really recommend to read this paper. It's an amazing paper, and these really basic papers are very worth to read. And in this paper, he wants to understand how the flow of water through a channel works. And he states two main questions. And one question is the philosophical problem. The philosophical problem is why gets flow unstable and changes from laminar to turbulent. And this question is till today not fully answered. So the why question, why this happens. And the second question he stated is the practical problem. And this is, I don't care why, but under which conditions, so at which velocity, at which diameter turbulent appears. So for the practical problem, you don't need the philosophical problem to be solved. The why doesn't matter here, but the why is the main question, right? Why this happens. So, and in his paper, he was able to find solutions. So here you see the pictures from his experiments. He used colored water in a transparent channel, and then he changed different properties like the velocity, the diameter of the channel, viscosity, and density. And he realized that the change from laminar to turbulent flow is not only dependent on one variable, but it's a dependence of a combination of different variables. And he stated this combination, it's a dimensionless number, in his paper, and afterwards it was called the Reynolds number. Okay, so the Reynolds number basically it's dimensionless, and it tells us if we have a laminar or a turbulent flow, and it's influenced by the velocity of the fluid, the density of the fluid, the size. The size could be the size of a particle, or here the diameter of the channel, so it's a characteristic length, and the viscosity of the fluid. And what was amazing in a channel, he measured at the transition point from laminar to turbulent flow at a Reynolds number of around 2300, and this is still valid today. So he made very, very good measurements and predictions. So this Reynolds number is very important. We have the velocity in here, we have fluid characteristics in here, and we have the diameter of the channel or the diameter of the particle in here. And if we take now a look at the Reynolds number for CD, because CD is a function of Reynolds number, so we can increase the Reynolds number, we can change it from low to high, and this would also change the drag coefficient, right? Because there's a dependency. And what you see here is one of the best measured diagrams we have in fluid dynamics, and this is the drag coefficient as a function of the Reynolds number for a spherical particle. And there you see this is a very complicated behavior, and you see why we cannot put just one equation in the drag force, because the shape of this behavior is so complex that you don't find just one expression to describe this full graph, right? Therefore, this is why we generally have to write CD as a function of the Reynolds number. But what we can do is we can put it in slices. We can look at different parts. And if we look at the first part, this is below Reynolds 1 or sometimes below Reynolds 0.25, depends on the book. And in this area, we have a laminar flow around the sphere. So the flow comes from here, the fluid comes from here, and we have a laminar called on flow and a laminar off flow. So complete laminar flow around the sphere. And in this area, we have a straight line. And a straight line can be described by an equation, right? So if we put a straight line here, we can describe this by 24 divided by Reynolds. So if we take a look at 1, right, Reynolds 1, if we put a 1 here, CD should be 24. So we put Reynolds 1, we take a look, 24. Until here, this very, very simple expression is the function of the Reynolds number. So CD equals 24 divided by Reynolds for Reynolds smaller than 1 in this area. And now we can take a look again at the drag force, and the drag force is density divided by 2. CD as a function of Reynolds, then we have the cross-sectional area and we have the velocity square. And now we said if the Reynolds number is smaller than 1, then we can put 24 divided by Reynolds in here. And if we put this in here, we just can rearrange the equation. So now we have 24 divided by Reynolds, and Reynolds is velocity times density times particle size divided by viscosity. And now we can calculate a little, or we can do the math a little bit, right? So we have 24 divided by 2 divided by 4. We have dp and we have dp squared, so 1 dp goes away, so we have dp left. We have a velocity squared, so 1 velocity goes away. We have this below, so this goes up, and if you do the math at the end, you will also here the density cancels out, right? And we will get a very, very simple expression for the drag force, and this is 3, so 24 divided 2 is 12, divided 4 is 3, pi, viscosity, particle size, and velocity, right? And this is also the drag force we used in the previous video to calculate the settling velocity, because for settling we assume Stokes regime. We assume slow settling, so a low Reynolds number. And in this part, in this Stokes regime, the friction term dominates the drag force. So in the beginning I said drag force is a combination of pressure and friction. And in a very low flow, or slow flow, sorry, we only have the fluid friction on the surface. There's no pressure, or very, very low pressure area. So this means that at low Reynolds numbers, the friction dominates, and if the friction dominates, the Reynolds number is proportional to the velocity. Okay, and this is friction term. So low velocity, friction dominates, and then the drag force is proportional to the velocity. So if we increase further the Reynolds number, now we are in a regime from Reynolds 1 till Reynolds 10 to the power 3. So we have here this little bit weird behavior. Now something changes in our flow. The on flow is still laminar. Okay, so we have still a laminar on flow here, but at one point, I didn't put the laminar lines in here, but we have the laminar on flow as in the picture before, but now something happens. Now the flow detaches, the streamline detaches from the particle surface because they are fast. And if they detach, they go away into these directions, and that means we have no streamlines in here, and this means we have a low pressure area because the streamline goes here around the sphere. We have friction, 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 and then it goes away. So, but if no streamline goes in here, we have a low pressure area, and this means we have a force pulling the fluid from here to here, and this is how we create these eddies, right? And these eddies go behind the sphere, and this creates a suction here, okay? So this is now a low pressure area, and now we have a pressure difference, something we don't have in Stokes regime. And to describe this area, we only have some empirical parts. So you have the data, you put an Excel fit into it, and you get this equation, which is basically a very easy empirical equation, right? And yeah, that's not very satisfying, but we have a lot of these different empirical equations for this regime. But important to keep in mind, here now we have also a pressure difference. Okay, so if we go further, we increase the velocity more and more and more. The Reynolds number increases more. We have this area from Reynolds 10 to the power 3 to Reynolds 10 to the power 5. And in this area, now the streamline comes in laminar, but detaches much earlier than in the area before. So we have a huge low pressure area behind the particle, right? Again, the streamline detaches, goes away from the surface, so there's no friction of the fluid on the surface, but there's under pressure, and this is why the fluid is sucked into here, and this is why we have a low pressure area which holds back the particle from the back. Okay? And in this area you can see that the CD is nearly constant, so you can make a straight line, and this straight line goes to a value of 0.44. So CD is 0.44. And this makes the calculation very easy, because again we have the drag force, we need something to put in here, and this is 0.44. And if we do put the 0.44 in here, we do a little bit the math, we get again a very simple equation, which is 0.17, right? All the calculation, the pi is now considered. Density of the fluid, dp to the power square, and v square. And this is now fundamentally different, because now the drag force depends on the square of the velocity. And this is due to the influence of the pressure difference. Okay, so in the equation before, we didn't have the density of the fluid in there, we had the viscosity of the fluid, right? Viscosity of the fluid is friction, and then we have dependency to the velocity, and now we have the pressure difference, right? If you look at this picture, a huge area of pressure difference, and the pressure difference goes with V square. Okay, so for this quadratic regime, velocity square, or also called Newton regime, the pressure difference is the main part of the drag force, and this is why in this regime the drag force depends to the velocity square. And this dependency was already derived by Newton. This is why we call this quadratic regime also Newton regime, because Newton made at his time some theoretical calculations of the drag for spheres, and his practical application at his time were to calculate how the flight of a cannonball. This was his practical interest at this time. And by even if his approach was not correct, because he said that the cannonball is stopped by molecules hitting the cannonball, he ended up with drag force is proportional to V square. And this is why we also call this Newton regime. Okay, and here we are already at the end, so I hope you learned the general drag equation, how it's set up, what are the variables in there. I tried to talk a little bit about the Reynolds number, where it's coming from, what's its importance, and what is in the Reynolds number, and then you learned about the drag in different flow regimes, and therefore it's extremely important to keep in mind that the drag is an umbrella term with friction and pressure difference, and at low Reynolds numbers, so at low velocities, we have completely laminar flow, so we have friction, and the friction is the drag force depends on the velocity, and then if we increase the velocity, we increase the Reynolds number, the fluid detouches, we get a low pressure area, so a pressure difference, and then we have a dependency of the drag force to the velocity square. With this, I'm finished with the video. If you have any question, please let me know, and thanks for watching the video.